Hello, everybody. My name is Alexander Jung. I'm an assistant professor for machine learning at Aalto University in Finland. In this talk, I want to discuss an information-theoretic approach to obtaining personalized explanations of machine learning methods. Machine learning is all around our daily lives. We routinely ask our smartphone to tell us the best pizza place nearby, or to translate simple text snippets from or to foreign languages. Many of this and similar tasks are already satisfactorily solved by smartphone apps that use machine learning methods. Sometimes the abilities of these machine learning methods seem like pure magic, and their inner workings are hard to grasp. In this talk, I will discuss one approach for getting explanations of the behavior of machine learning methods. We will try to answer the question, how does this machine learning method work? Maybe the most thorough approach to explaining machine learning methods is by teaching them at universities. I am teaching some university courses on machine learning at Aalto University. And these courses also belong to whole study programs for machine learning. Indeed, nowadays, many universities offer, for example, master programs in machine learning. And I would consider the most thorough form of explaining machine learning by teaching machine learning principles to students during such master level programs. However, machine learning methods enter so many diverse application domains that we simply cannot expect anymore the machine learning user or the user of the machine learning method to have the time or even the opportunity to complete a master program in machine learning. Consider, for example, wine farmers, which might benefit or might use machine learning methods to help in their decision making. We cannot expect a wine farmer to first complete a 2-year master program in machine learning before starting to use these methods. So let us stick for the time being with the application domain of wine farmers and assume that machine learning methods could be used to predict the yield that can be expected in a given wine harvest. So how would that work? A machine learning method could aim at learning a predictor map or a function that reads in all the characteristics of a wine harvest, like the biochemical properties of the soil or some information about the grape variety, and also the time of harvest or the planned time of harvest might be a relevant parameter or characteristic. And after we feed all these facts or characteristics or features into the predictor map computes or outputs an estimate for the yield that we can expect. For example, in this case here, the expected or predicted yield would be 2,000 liters of wine. The principle of machine learning, or used within machine learning methods to obtain such a wine harvest or yield predictor, is quite simple. The idea is to find relevant patterns in previous examples, which we call training examples. Roughly speaking, machine learning computes or constructs a predictor map for the yield by extrapolating from previous wine harvests. So let us depict the previous wine harvests in a massively simplified form as dots in a plane. The horizontal axis of this plane represents the feature values of a wine harvest, and the vertical axis of this plane represents the values of the wine harvest yield. And each dot in this plane represents a previous wine harvest. And the vine harvest is characterized by the coordinate on the x-axis, which is given by the features like the soil properties or the time of harvest. And the previous vine harvest is also characterized by the yield that we obtained, which is the y-coordinate or the vertical coordinate. And then machine learning methods do nothing but fitting a curve out of a predefined set of curves to these data points. So this curve represents the predictor map. We can evaluate the curve for any possible features of a wine harvest. Also for the features of a wine harvest for which we don't know yet the yield and actually want to predict the yield for this wine harvest. The important point here is that machine learning methods differ in the choice of curves or classes of curves they allow for this fitting. For example, deep learning methods use deep artificial neural networks to represent such highly nonlinear functions. So what machine learning does in the end is fitting a highly nonlinear curve to many high-dimensional data points. Here in this simplified diagram, I have illustrated only one feature, which is given by the x-axis, but in practice, we collect thousands or even billions of numbers or characteristics of a wine harvest. We could take the biochemical properties of the soil at every square centimeter if we have the time and resources for this. And after we have learned the predictor map by fitting to the previous wine harvests, we apply it to a new data point, like the wine harvest that is coming up this year. And the application of this predictor map yields the predicted yield or results in a prediction of 2,000 liters of yield. And this whole workflow of machine learning has been applied very successfully in several applications. For example, in recommender systems used in streaming apps, this principle of learning a predictor works exceptionally well. However, as machine learning methods become increasingly relevant or interesting for application domains which involve critical tasks, critical in terms of putting humans at risk, putting the life and the health of humans at risk, we need to ask for more than just a high accuracy or good statistical properties of a machine learning method or a predictor. Consider, for example, autonomous driving, where a machine learning prediction might decide if the car hits a person or not. And in this case, we need to have reliable methods and accountable methods. So we need to be able to get some understanding why certain predictions that led to decisions arose. And here it is crucial for machine learning to be accepted or to be accessible at all in these critical application domains, to have explanations for the predictions obtained from the machine learning method or machine learning model. So consider the machine learning prediction here for the wine farmer. The prediction might be 2,000 liters of wine for the yield. And then the farmer, which might not be a machine learning expert, might ask why. Why do we have this prediction of 2,000 liters of wine for the yield? And what can we offer the wine farmer here as an explanation for this prediction? So in order to provide an explanation, we need to first be clear about what do we want from an explanation, or what do we want an explanation to be. So I have found here one definition for the term explanation in an online dictionary, which states that an explanation is the details or resources or reasons that someone gives to make something clear or easy to understand. I have tried to come up with a bit more technical and a bit more precise definition of what we mean by an explanation. And in particular, I define an explanation as some artifact that reduces the level of surprise caused by a machine learning prediction. And an artifact can be anything that is able to carry information. So an artifact might be any object, for example, an icon. So if we show the user an icon, this might be an implementation of explainable machine learning. So providing an icon, choosing an icon out of a set of different icons, of alternative icons, might act as an explanation. Another example for an artifact that can be used as an explanation is a reference example. So we might explain the prediction for the yield by pointing out a similar harvest last year, which had similar characteristics, like the soil properties were similar and the temperature around the harvest was similar. And then in this previous wine harvest, we achieved the yield of around 2,000 liters. And that's why now the prediction is again 2,000 liters. Another example for an explanation might be pointing out certain features which are most relevant for the prediction. So one explanation could be for the prediction of 2,000 liters yield, because the average temperature in May was around 20 degrees. And based on this model that we used, this average temperature resulted in a prediction of 2,000 liters. Another very important example for explanations is counterfactuals. So we could explain the prediction of 2,000 liters yield by pointing out how this prediction would change if certain conditions would be different. For example, if the harvest would be 2 days later, the yield would be more, would be 2,500 liters. And this explanation, this type of explanation is very popular or useful because it implicitly points out actions or decisions that the user, the machine learning user, in this case the wine farmer, might take. So if the counterfactual points out that 2 days later, if we would change the time of harvest to 2 days later, the yield would increase, then we might actually do it. We might harvest later. So counterfactuals show that an explanation can also help the user for decision making, or make it even easier or more convenient to go from the prediction to a decision or decision making. So let me recapitulate, let me repeat again the motivations or some motivations for taking the effort to construct explanations of machine learning predictions. So what I said, they increase and they simply are necessary to have acceptance of machine learning in exotic domains. By exotic domains, I mean application domains where the users of machine learning methods simply do not have a formal training in machine learning or even applied statistics. So a wine farmer might be hesitant to using machine learning methods because he or she does not understand how these methods work. And providing explanations, higher level explanations, might help to improve the acceptance in such domains. And as I just discussed in the context of counterfactual explanations, providing explanations might point out immediate decisions or how the system should be changed. For example, the counterfactual explanation in the wine farmer example suggested to decide for a harvest 2 days later. Then also a very important point or aspect of providing explanations is that it might boost the interaction between the human user and the machine learning method. I will then discuss an example with the wine farmer where the explanation might point to a weakness of the model, which can be identified by the human expert and might lead to an improvement of the model. Let's illustrate this by the wine farmer example. So assume that the machine learning method predicted the yield by 2,000 liters, and the farmer wants an explanation. So the farmer asks, why? Well, the explanation of the machine learning method is because there was a similar harvest last year. So the machine learning points out to a related harvest or a harvest that the machine learning method considers similar and which resulted in a 2,000 liter yield. And based on this explanation, the user, in this case the wine farmer, might realize that in this reference example, so the similar wine harvest, there was a big difference to the condition now to this data point, the current wine harvest, because in this reference wine harvest, there are no birds. So the specific of this wine harvest is that there's a large population of certain birds which can damage the harvest. And so this explanation here, providing the explanation, resulted in the user pointing out a weakness of the model. In particular, the prediction model didn't take into account population of birds. So we might then go back to the machine learning engineer to improve the model by also taking into account certain biological properties, like the presence of large populations of certain birds. To now, our discussion of explainable machine learning was rather informal and on a very high level. To obtain a more principled approach for constructing optimal explanations, we will use a simple probabilistic model. Within this probabilistic model, we interpret the prediction y hat obtained by a machine learning method, the user knowledge or user summary U, and the explanation E, as well as the features of a data point as random variables. In particular, we model the user summary, the explanation, and the prediction of the machine learning method as a deterministic or stochastic map applied to the features of a data point. This model is fully specified by the joint distribution of all random variables. Let us, for the time being, assume that we know this joint distribution for this model. In this probabilistic model, we can formalize or characterize the level of surprise caused by a machine learning prediction via the entropy of the prediction y hat. More precisely, we use the conditional entropy of the prediction given the user knowledge or user summary to measure the level of surprise caused by the prediction. Note that this measure, this conditional entropy, depends on the user summary U. So the more knowledge a user has, the smaller we expect this conditional entropy. So the smaller is the surprise caused by a machine learning prediction. We will see later a simple computer vision application where the user knowledge is the fact that the grayscale level of a given pixel can be well approximated by the average of the grayscale levels of the neighboring pixels. Using the conditional entropy as a measure for the level of surprise caused by a machine learning prediction lends naturally to an optimization criterion for optimal explanations. In particular, an optimal explanation should reduce the surprise inherent to a prediction as much as possible, or equivalently, an optimal explanation, which we denote E star, should maximize the conditional mutual information between the explanation and the machine learning prediction, conditioned on the user summary or user knowledge U. Note here that the optimal explanation E star might depend on the user. So for different users, which are characterized by different random variables U here, this optimization criterion is different. So we might end up with different solutions, with different optimal explanations for different users. Hence, our approach delivers personalized explanation. Note also here that we restrict the space of possible explanations to a subset calligraphic F, which we call the set of allowed explanations. This is somewhat similar to the concept of a hypothesis space for machine learning methods, where we need to restrict the space of allowed predictor maps for computational reasons. Similar here, we need to restrict the set or the space of all maps that deliver an explanation to a subset which we denote calligraphic F. In order to obtain a practical algorithm, so to actually compute these optimal explanations, we need to estimate or approximate the conditional mutual information. And we can estimate this conditional mutual information, for example, using training examples or IID training data points of these machine learning predictions, of the user summaries, and the features of data points. Moreover, we will also restrict ourselves to explanations that are obtained by linear maps. And moreover, this linear map, which is characterized by a weight vector W, might only have up to S, where S is a sparsity degree, non-zeros. So this S is a fixed constant, a small constant, which gives the maximum number of non-zero weight vectors, or equivalently the maximum number of features which can be involved in the explanation E. It turns out then, under these modeling assumptions, the problem of computing optimal explanations reduces to a sparse regression problem. And we can solve such a sparse regression or lasso problem quite efficiently using modern convex optimization methods. So there is much work on how to solve such sparse linear regression problems involving big data. And the output of this algorithm is a set of features, or the support set of this weight vector beta. And this subset of features is used as an explanation. So the output of this algorithm is a subset of features that are most relevant for explaining the prediction of the machine learning method. Note also that this algorithm is model agnostic in the sense of not requiring any information about the inner workings of the machine learning method that delivers the predictions. So we only require examples or IID samples of machine learning predictions. So we only need to probe the machine learning method for some training examples, but we don't need to look inside the machine learning method to implement our algorithm for computing explanations. To illustrate our algorithm for computing explanations, we consider the problem of analyzing road marking conditions in the Helsinki city area. So the city planners of Helsinki city are interested in automated ways to analyze the quality of pedestrian crossings all around the city area. And to this end, they collect a large amount of aerial photographs of the city area, which can then be analyzed using machine learning methods. For example, a subtask in this application is to learn a predictor of the grayscale level of a certain pixel, pixel I, which is the target pixel here. And we want to predict the grayscale level of this pixel based on the grayscale levels of the neighboring pixel. So in the pixels in the neighborhood, which is denoted calligraphic PI here. And we can then use our algorithm to compute explanations for this predictor that we can learn using some general purpose machine learning method. And we consider two specific users or two types of users. We have a user A, which is having no computer vision knowledge. And we model this by using a constant as the user summary, a fixed constant. And in this case, our algorithm delivers as optimal explanation the two immediate vertical neighbors of pixel I. So the best explanation for the predictor of the grayscale level of pixel I is given by the immediate vertical neighbors, which is somewhat reasonable for somebody who has a computer vision knowledge. For like user B, which we assume to have some computer vision background. And this user B considers the local average of the grayscale levels in the neighborhood of the pixels as a good indicator of the grayscale level of pixel I. And for this user B, our algorithm determines as the optimal explanation the second degree neighbors or second hop vertical neighbors, which are indicated by these green rectangles here. So as you see, for different users, we get different explanations for the grayscale level predictor. And these explanations in this case might hint at the vertical directions or vertical neighborhoods being more informative for the properties of a pixel compared to the horizontal neighbors. So let me wrap up my talk. We have formalized the computation of optimal explanations using a very simple probabilistic model. In this model, the effect of providing an explanation amounts to revealing a random variable. This random variable represents the explanation. And revealing this random variable reduces the conditional entropy of the machine learning prediction. And this makes sense since we use this conditional entropy to quantify the level of surprise caused by this prediction to a user. We then construct optimal explanations by solving an equivalent problem of maximizing the conditional mutual information between the explanation and the machine learning prediction. And in order to implement this optimization or to solve this optimization problem, we need to estimate the conditional mutual information, which might be done from IID samples or training samples of the features of data points, the machine learning predictions, and the user summaries. In particular, our method does not require any information about the inner workings or inner logic of the machine learning method. It only needs snapshots of the machine learning method in the form of IID samples or realizations of the machine learning predictions. We have only scratched the surface of the information theory for explainable machine learning so far. One immediate extension of our approach would be to consider nonlinear machine learning models. We would also like to study counterfactual explanations within our information-theoretic approach. And this is also related to the more general question of how to choose or are there principled ways to choose the space of allowed explanations? Similar to the hypothesis space underlying a machine learning model, we need to restrict the space of possible explanations in order to obtain user-friendly and computational feasible explanations. As I have indicated during my talk, one of the reasons for providing explanations is to maximally engage or empower the machine learning user and, for example, help lead him to improving the model by bringing in domain expertise. In the wine farmer example, the user or domain expertise was the knowledge about large bird populations that were not present in the training examples used for the machine learning method. And so far, we do not have a principled approach to model this dialogue between the machine learning user and the machine learning method. You can find more details about the concepts that I have discussed in this talk in the recent paper that has been published in the IEEE signal processing letters. And the preprint of our paper is also available on the archive. Thanks a lot for your attention.
Hey everyone, we're back from Alexander's talk. Alex, thank you very much for the presentation. It is in fact very true that the topic of explainability is extremely important nowadays. And by the way, probably especially so to Alexander, because he gave us a little bit of a confession, and I must share that with all of you. He told us that his current job and spouse have to some extent been chosen by ML algorithms. So there you go. I wonder how many of us have probably been a part of that group sometime in our lives. I hope nobody is looking for an explanation for that though, so hope everybody's satisfied. So Alex is now joining us again for Q&A, and we'll be reading directly from the questions you have been posting online, okay, based on the number of upvotes. So you can keep the questions coming, and we'll just be reading them. So Alex, first question. Do you consider that terms interpretability and explainability in machine learning are the same? What's your view?
Yes, so to some extent, interpretability and explainability can be used synonymous and refer to very much the same thing. I would say they refer to different ends of the usage, or to different ends of the communication channel between machine learning algorithm and user. An explanation is provided by the machine learning algorithm or by the explainable machine learning algorithm, and the interpretation then happens in the brain of the user, hopefully. But of course, in order to be interpretable machine learning method, it needs to be an explainable machine learning method. So from this perspective, I would consider them synonymous.
Okay. Yeah, I guess it's more of a difference in semantics and in who is reading what, right?
Yeah.
Okay. Cool. Next question. What's the difference between your proposal and just checking the contribution of each feature to the model output? What are the advantages?
So the approach that we are using is more general. So as a special case, we can get explanations in the form of a set of features, which we actually do in our paper. We consider a toy example related to computer vision, where we want to find the most important pixels for a prediction task. So selecting features for an explanation is a special case. But this information-theoretic approach allows for way more general forms of explanations. As I tried to explain in my talk, we can use any artifact, anything that can carry information as an explanation. This can be a subset of features that are most relevant, or it can be a reference example. So this would be an explanation by an analogy, which I used in my wine farmer case, where the explanation was pointing to a similar wine harvest in the previous year.
Okay. Okay. Cool. I was actually thinking about it as you were speaking, and yeah. Okay, it makes sense. I don't have any follow up on that. I'll just go right to the next one. There's someone asking us about how domain knowledge can have an impact on explainability itself. So one question is, can the lack of explainability be mitigated also by developing data scientists with domain knowledge? I guess the answer will be yes, but if you could give us a little bit more of your opinion on that.
Yes, so as our approach makes it somewhat explicit, the explainability depends on who is using, so the particular user. And explanations need to be tailored to users. And if a user has more background in data science, knows about generalization, knows about probability distributions, then we can use different, more powerful explanations. So one way to improve explainability could also be to train the users more, like the wine farmer, to include data science courses in curricula for farming degrees. I guess, I don't know, but I'm pretty much sure that this is already done. So wine farmers might already take courses in basic data science.
Okay. I was reading here. Okay, I guess this is the elephant in the room of questions in terms of explainability, which is about Lime or SHAP, which are, in my opinion, the state of the art for explainability models. What's your opinion on them?
Yes, so I consider this Lime in particular as a industry standard, so to say, regarding the broad usage of this method. Yes, so as a starting point, one should always consider Lime as a baseline or for a benchmark.
Okay. Have you ever done anything with SHAP, by the way?
No, not yet.
Okay. No. Okay, cool. Changing the topic a little bit, is there any app besides Excel or Weka to be used by a wine farmer in an easy way without a great knowledge of machine learning?
Well, I just Googled when I saw this question, and I found immediately a post on applying standard deep learning to predicting harvest yield. So one of the main drivers for this deep learning hype is that it becomes very convenient now to download a library like Keras for deep learning models, train it on your own data. Maybe you have collected some data using your own sensing devices, and you can implement the machine learning method yourself. So it's deep learning is almost as convenient now as using Excel. But anybody which uses a weather forecast makes use of predictive models of machine learning to some extent.
Okay. I guess it doesn't have the same barrier to entry, though, no? For the case of a wine farmer.
No.
Okay, cool. Let me just check the time. Okay, we have 1 minute left. Let's try to pull another one here. So working on a natural science domain, I get the question why a lot. What is your recommendation for applications where explainability is a must? Go for the parsimonious approach. Try to convey hybrid approaches that combine ML and mechanistic models. This was a bit long. I don't know if you want me to repeat.
Yeah, no, it's okay. So I don't have a clear-cut answer for this. The type of explanations, this is a design choice. Mm-hmm. So as we already discussed, an explanation could be a subset of features, or it could be a reference example from the training set, or it could be a law text. So decisions in court cases, I guess court or AI for law is such an application where the why is a must. Each court decision must be argued. There must be an explanation. And for this, I see that we need to bring in more, for example, natural language processing. So we need to produce explanations as highly codified text, like a legal text. Yeah, but in general, I don't have a clear-cut answer for this. So there are so many different domains, and this needs the cooperation of domain experts, of machine learning scientists, and now our approach also brings in information theory, experts, which is, of course, goes already to machine
sorry
learning.
for interrupting you. I guess like the biggest proof that you can have that that science domain is important is the fact that you cannot give a ready to go answer. It really needs to be ad hoc depending on the application, right?
Yes.
Okay, cool, Alex, thanks. I'm gonna have to wrap this up because we're actually 1 minute over and we're running out of time. Let me just tell everyone, please don't hesitate to keep this conversation flowing with Alex outside of the talk. And for that, you can, I encourage you to all to use the event platform to chat, okay? Alex, thank you so much again. We'll now go to a break and we'll be back in 10 minutes. There will be a live sketching session happening as well as videos from our sponsors, guys, okay? So you can stay in the live stream or you can also explore our event platform and participate in the activities, okay? See you in a bit. Thanks, Alex, again.